original vectors. So we have a spanning set originally of 4 vectors. We found these 2 relations, which are exactly the same from these 0 rows appearing in our Hermite normal form algorithm. And from them, we're able to extract these 2 relations, that this equals 0 and this equals 0. So it's a very efficient use of this algorithm. We're using all parts of the algorithm now. First of all, to obtain the basis itself, and then to obtain the relations, or at least some sort of defining relations that characterize these original 4 vectors. So to summarize what we just did, we started out with these 4 vectors, labeled 1, 2, 3, 4. We found out that the integral linear span of those 4 vectors is the same as the integral span of these 2 vectors. So we found a basis for this integral linear space. And we established that the relations satisfied by these 4 vectors include these 2 particular relations corresponding to the 2 rows that we obtained during that algorithm. So the number of relations that we obtained here corresponds to the number of 0 row vectors produced in our Hermite normal form algorithm. If we had obtained 7 row zeros during the course of a more complicated algorithm, then we could deduce that there had to be 7 of these sort of essential relations, or basis relations almost, satisfied by whatever original spanning set we have. And the number of relations here then corresponds to the difference between the number of vectors in the original spanning set, in this case 4, and the number of vectors in the final basis. We start off with a certain number of vectors in the spanning set. We do our row reduction algorithm. We obtain a certain number of 0 rows. Each one of those 0 rows corresponds to essentially dropping a vector from our spanning set. So the initial spanning set and the final minimal spanning set, the difference between those 2 is exactly the number of relations that we're obtaining this way. So 4 minus 2 is the 2 that's counting the number of relations. This relation between these quantities can be rewritten in this way, that the number of vectors in the original spanning set is equal to the number of vectors in a basis plus the number of relations that we're getting. So if we start with 4 vectors in the spanning set, and we end up with 2 vectors in our basis, then there will have to be 2 relations to make these in balance. It's a kind of easy consequence of the way the algorithm works. This is, in fact, our version, in this context, of a very important theorem in linear algebra. It's called the rank nullity theorem. We'll talk about that a little bit later in our next video. Okay, but it's a very important relation that here we can see a very direct and kind of obvious, almost, manifestation. Okay, this is nothing deep or mysterious about it. We're just reducing the number of vectors in our spanning set by obtaining 0 rows, and we're counting the number of 0 rows. That's how many relations there are. But the way we phrase it is really not the complete story, because it's not really that there's exactly 2 relations satisfied by our 4 vectors. And the reason is because, as we've seen before, a linear combination of relations is also a relation. So if we look at the 2 relations that we've established, this was the first one, this was the second one, we could perhaps represent these relations by recording these coefficients as kind of a natural thing to do. So that first relation kind of corresponds to the numbers 42, 7 minus 49, 1. We can perhaps bring those together in a list, or another kind of vector, and maybe we could, say, use pointed brackets to, in our mind, separate the role of this kind of vector from the other vectors that we're considering. The second relation, 22, 1 plus 4, 2s minus 25, 3s, would be represented by this relational vector, 22, 4 minus 25, 0. Okay, but we could take these relations and we could form combinations of them. For example, we could add these 2 relations, getting this one here, which corresponds to just, of course, adding the corresponding relational vectors. 64, 11, minus 74, 1. Or maybe we could take the difference. First relation minus the second relation, and we get this one here. Which would correspond to just the difference between these relational vectors. 42 minus 22 is 20, the difference here is 3, the difference here is minus 24, and 1. And of course we can take more complicated linear combinations as well. So the relations themselves form an integral linear space. This is a useful and important understanding. That the relations themselves form an integral linear space, in some sense. We have these sort of 2 basic ones, but integral linear combinations of them are also relations, so also deserve to be included in the sort of relational space satisfied by our 4 initial vectors. Okay, so how are we going to put our finger exactly on what's going on here in terms of the relations satisfied by an M set of M sets? We want to set up some notation that effectively captures this language of relations and allows us to talk about relations as objects themselves. So let's look at an example to try to orient ourselves. Here are 3 M sets again. They're, in terms of some history, symbols, X's, and squares. So they just stand for some priorly defined mathematical objects, which we understand completely. Okay, so here's A, which is x square x. Here's B square square x x x x. And C is x square x square x square x square x x x x. I'm mixing things up a little bit just to remind you that these things really are unordered. We don't always have to insist on all the x's being together and all the squares being together and so on. Right. Okay, what relations are satisfied? Well, it's a relatively simple situation because it turns out that 2 times A is equal to B. And A plus B plus A equals C. Okay, that's just a long-winded way of saying that 2A plus B equals C, but it's, it's still a valid kind of equation. And C is equal to 2 times B. So these are amongst the relations satisfied by these 3 sets. Okay, so we'd like to introduce a kind of an object that captures these relations. So let's try something like this. Let's try to define a space initially. Say rel for a relation. Rel of A, B, C. Here we have 3 m sets, the m set of those 3 m sets, and we're interested in the relations satisfied by these 3 m sets, A, B, and C. Okay, if we look at these relations, we can see that this one here is really a consequence of these two. Because if C equals 2B and 2A equals B, then this here, this 2A is really the same as B. And so this left-hand side is really B plus B, which is 2B. That equals C. That's just a repetition of this one here. This relation is not really different or separate from these two themselves. So in terms of a minimal defining relational set, we can say, okay, 2A minus B and C minus 2B are perhaps some kind of minimal relations. So we can think about that. We can think about creating an M set consisting of these expressions, 2A minus B and C minus 2B. That kind of perhaps captures the relations, or at least the sort of spanning set for the relations between A and B. Okay, so there's a question mark over here. This is a preliminary kind of attempt. Okay, trying to set up what we might mean by the relation satisfied by A, B, and C. And the natural question is, does this work? Is this a satisfactory answer to what we want to do? So there's a good opportunity here for you to do a little bit of exploration. I'm going to give you a very interesting exercise at the end of the next slide. So something to think about in terms of sort of structuring mathematics, some structural, challenging question ahead of you. But you might already start thinking here, does this work? I mean, is this a satisfactory kind of setup of trying to capture the relations formed by these 3 m sets? So begin that thought. And I hope that you agree with me that this original attempt, this first attempt, is really not very successful. Defining relations of A, B, and C to be this M set consisting of the expression 2A minus B and C minus 2B is not really a good definition. For 2 reasons. First of all, since if you actually think about this expression 2A minus B, okay, this has a prior meaning, because A and B are explicit M sets. So 2A minus B, that's something that we already have a prior meaning to. That's a linear combination of the M sets A and B. And in fact, we know that that linear combination is actually the empty M set. Similarly, we know that this combination is actually the empty M set. So if we're going to write something like this, then someone else is allowed to come along and say, wait a minute, this thing here is actually the empty M set, as is this thing here. So what you've really written down is relations between A, B, and C is the M set consisting of 2 empty M sets. And once you write it this way, then it becomes vacuous. You're not saying anything anymore. The second reason why this is not such a good idea is because it doesn't distinguish between these 2 relations, especially these 2 relations, and other possibilities. For example, if we had replaced this one here with the equivalent one, A plus B plus A equals C, it's a little awkward, but it's still generating the same space of relations, then this looks different from this. So this is an initial stab at defining the relations between a bunch of M sets, but it's not a satisfactory resolution to this question. So I'm going to leave this to you now as an exercise for the next little while, so our next video. I want you to think about how you might set up a theory of relations amongst M sets. Anyway, this is a very fundamental question. Again, the M sets in mathematics. Here we have a bunch of M sets. We've written them down. We'd like to describe the relations satisfied by these M sets. We'd like to have a consistent and clear notational convention for how to describe and get at and specify the relations satisfied by these given M sets. Okay, so it's such a very, very fundamental kind of thing that we want to do. And how are we going to exactly do it? So I'm going to give you my solution next time, but I think it's really great for you to think about this yourself. How would you go about it if you had to define this thing? You know, what is the definition of rel A, B, C going to be? In a way that effectively captures what we want from the relations between these 3 M sets, or more generally, a bunch of M sets, a multi-set M sets. So a bit of a challenge for you to have a go and see if you can come up with a good definition. We'll come together and share our views with our next video. I hope you'll join me for that. I'm Norman Walker. Thanks for listening. I'm Norman Wahlberger from the University of New South Wales, and in this short little video I want to tell you about our upcoming professional development course for high school math teachers, but which might be interesting to a wider audience as well, including high school students. So the course is called Linear Relations and the Geometry of Lines, okay? And it's notably a professional development free online course. So you can join up and enroll for free, and it's going to be open for quite an indefinite amount of time, so there's no hurry. It's operated by the School of Mathematics and Statistics at the University of New South Wales, Sydney, and I'm the presenter of that course. Okay, the audience is high school math teachers wanting to strengthen their understanding of a really quite fundamental aspect of high school mathematics, the idea of linear relationships and how they're algebraically and geometrically represented by linear equations and lines in two-dimensional Cartesian plane. So it's very basic, but kind of fundamental technology that students and teachers who are teaching those students need to know about. And it's also interesting because it connects with actually a wide variety of interesting topics in the modern world, because linear relations or direct proportionalities figure so prominently in modern life. Okay, the level is approximately that of the years 10 to 12 high school. So in New South Wales, this would correspond to, say, general maths or 2-unit maths, somewhere in that ballpark. But it's not inappropriate for a primary school teacher, for example, to take this course, or also for more senior teachers doing the extension level things. They'll also find things in there that are quite interesting for them. So this is actually the first of 4 courses that we are planning to offer this year. The 4 courses are all under the umbrella of mathematical relations. Okay, and the first one is the one that we're running, starting actually on Monday, linear relations and the geometry of lines. And then the next one is going to be quadratic relations and the geometry of a parabola. So kind of upping the ante, moving to a higher level, from degree 1 to degree 2, more complicated geometrical relationships, still very important in physics and in the other areas of mathematics. And then inverse relations and the geometry of the hyperbola. Fascinating topic. That's really very important for calculus and other things as well. Lots of interesting applications to rather exotic kinds of laws that actually occur even in social sciences. And then our fourth course is power laws, polynomials, and why big animals live longer, which connects with more general kinds of relations that are in the direction of these ones, but a little bit more extensive, power laws, and they apply to a wide range of especially biological applications. Okay, so the first course is actually starting next week, but it's an open-ended kind of course, so you can just enroll and start and work through at your own pace. It's entirely free. The other 3 courses are not going to be free, so we are going to charge for that. So hopefully you'll find the first course so interesting that you'll want to sign up for the next course once they're available. And where do you find this very interesting course? You find it on Open Learning. Right? That's a very nice platform developed here in Australia for education that's quite wide and online and very interactive and sort of communication-oriented. So it's a very nice platform, and here's the actual URL for it. But if you go to Open Learning and you search for linear relations, then you will find it. And then you just enroll. It only takes 2 minutes, and on Monday you can start the course. And I hope that you'll be encouraged to ask questions and make comments and interact with other participants. It's a rather social platform, and it's designed for people interacting and sharing ideas. So I'm keen to find out how you like the course and what you think about it, because I'm thinking of this platform as being a useful one for us to think about other courses as well. All right, so check it out. Join up if you're interested. If you're a professional, development-oriented high school teacher, I really think that it will be a very valuable thing for you. I'm Norman Wahlberger. Thanks for listening. Good day, I'm Norman Wahlberger. In today's video, we're going to go a little deeper towards Hermite's normal forms. This is a very powerful technical tool developed in the middle of the 19th century by Charles Hermite, well-known French mathematician, that really gets lattices under control, lattice being the same as an integral linear space. And it's really the tool that we're able to use to compare lattices, to look at the relationship between lattices and all kinds of other fun things. Okay, so it's really all about integral row reduction, which is an integral version of what's often called Gaussian elimination or row reduction in linear algebra courses. So this will kind of bridge between linear algebra and abstract algebra. Naturally, those subjects are overlapping. Okay, so to illustrate the idea, let me go over one of the questions I gave you last time, which is to find a good basis for the integral linear span of these 3 vectors or vectors. Okay, so we have 3 vectors in the three-dimensional space. They form a lattice, which geometrically is something like this, extended in all directions. Okay, we want to understand that thing by replacing these rather complicated vectors that we start with hopefully circular vectors that span exactly the same lattice that we have currently. All right, so how do we do that? Well, we write down the 3 vectors and give them some names, and we're going to make certain reasonably simple, allowed moves to transform these into other vectors, still having the same property that they span the same space as we started with. Okay, so I'm going to illustrate the basic idea of heading towards what's called Hermite normal form. Okay, so we take our 3 vectors and we look at the entry in the first position. So we're looking at this first column here, if you like. We see a 4, a 6, and a -2. Now we ask ourselves, what is the greatest common divisor of those three numbers? The greatest common divisor is 2. Okay, so what we're going to do is we're going to attempt to get a new vector which has a 2 in that first position. And we can do that by, say, taking the difference between 2 and 1, or we just negate vector 3. So let's negate vector 3. So there's minus 3, which will give us 2 minus 5 minus 4. And that will be what we'll call number 4. And let's actually use a red pen to get rid of that 3. So we're replacing the 3 with the vector 4. So now that we have this 2, which is the greatest common divisor in this first position, we can add multiples of this one to these other vectors to actually get rid of the entries in that same first position. Because we know that these things are multiples of that one. So for example, to get rid of this 4, we'll just take vector 1 and we'll subtract 2 times row 2. So this one minus 2 times that is 0. This minus 2 times that is 6. This minus 2 times that is also 6. And that'll be a new vector 5. And we're replacing row 1. To get rid of this 6, we'll take row 2, or vector 2. We'll subtract 3 times. Well, I said 1 minus 2. I should have said 1 minus 2 times 4. There we go. And now we take row 2, we subtract 3 times row 4. Minus 3 times row 4. Okay, so 6 minus 3 times that is 0, as we expect. 0 minus 3 times minus 5 is positive 15. And 8 minus 3 times minus 4 is 8 plus 12. That's 20. There we are, 6th vector, and we are replacing the second vector. Okay, so whenever we add, here we're taking the vector 2 and we're adding a multiple of some other vector to it, it means that the second vector gets replaced. Okay, so we have these vectors now. And notice that there's only one that has something non-zero in that first position. The others have zeros in that first position. So we're kind of done with the first position, and now we move to the second position. Have a look at the second positions. But we kind of disregard this first vector because we sort of have that one nailed down temporarily. So let's look at the other two vectors, and we look at the second entries and ask what's the greatest common divisor of those two numbers, 6 and 15. The answer is 3. So what we're going to do is we're going to take a multiple combinations of these to try to get a vector which has a 3 in that second position. Okay, so how do we do that? We'll take row 6 minus, say, 2 times row 5. Okay, that will give us a 0. 15 minus 2 times 6 is 3. And 20 minus 2 times 6 is 8. And that will be number 7. And we take 6 minus 2 times 5, so we're going to get rid of 6. Now having that 3, which is the greatest common divisor of those two numbers, means that we can use it to get rid of the other one. This 6 we know is a multiple of that 3, so we can add a multiple of this to this vector to get rid of that 6. Okay, and that'll be what? So we'll take 5 minus 2 times this 7 here. To give us 0. Notice that the 0 doesn't change because there's 0 here and 0 there. That's already been sorted. But now the 6 minus 2 times 3 gives us another 0. And the 6 minus 2 times 8 is 16. So I guess that'll be minus 10. That'll be number 8. Okay, that's quite good. But by the way, we should get rid of the number 5, shouldn't we? Yes. So at this stage here, we have row 4, row 7, and row 8. And their leading entries are for the first 2, and then the 3, and then the minus 10. We might as well change that minus 10 to a 10. That's a little bit nicer, isn't it? So let's take minus 8. That will give us 0, 0, 10. And we'll call that number 9. Okay, so you can easily stop here. You can easily stop here and say this is a nice basis, and you'd be right. So this vector 4, vector 7, vector 9 would be a nice basis. But we want to go a little bit further to what's called Hermite normal form, which is a very particular kind of situation. Okay, so we need to do a little bit more. What we have to do is we have to look at the other entries of the vectors that we've gotten that correspond to the leading entries that we've obtained. So when we obtain this leading entry 3, we want to look back at the previous vector and use that 3 to adjust the second component so it's in a more reasonable range. Right now it's minus 5. But we can add any multiple of 3 to it. In particular, we can get it between the range of 0 and 2. Okay, so let's do that. Let's take number 4, and we'll add 2 times row 7, giving us 2. So that minus 5 plus 6 will be 1. And the minus 4 plus 16, minus 4 plus 16 is 12, yes. And that will be number 10. And which one have we gotten rid of? Well, we've added something to row 4, so row 4 is gone. Now, this entry, this 1 here, is less than 3, but still positive. We can do something a little bit similar with this 10 here. There's also a leading entry. We can use this 10 to adjust other ones if we want to. So we can add or subtract multiples of 10 to this 8 to adjust it, but we're not going to do it because we like that 8 is between 0 and 10. But this 12 is not between 0 and 10, so we're going to adjust it so that it is. So we'll take number 10, and we'll just subtract number 9, giving us 2, 1, 2. Let's remember that.